Yes, they're following you.
Good afternoon. My name is Jennifer Dill. I'm a faculty member here in the School of Urban Studies and Planning. And along with Rob Bertini and Chris Monsieur, fellow faculty members, we organize this seminar every Friday throughout the academic year. And this is our second to last of the quarter. Next week, we're going to have Carolyn Bonner, another one of our Masters of Urban and Regional Planning students, talking about her field area paper research on transit in small cities. In terms of logistics, just to remind everyone that we are being webcast, and therefore if you ask a question, please use the microphones in front of you and hold down on the button, and so the red light is on while you're speaking, so the people in the web can hear you. And we do have people listening on the web. And in fact, I just got an email today from people at Arizona State University who apparently watch us sometimes on the web. I hope that doesn't make you too nervous, Mike.
One of the studies I refer to is from Arizona, so it works out well.
Okay, so without further ado, I want to introduce Mike Rose, who's one of our Masters of Urban and Regional Planning students who's going to be graduating in a couple weeks. And he's going to be speaking this afternoon about a project that he's been working on for Rob Bertini about evaluating the Comet program. So without further ado, Mike.
Okay. Well, thank you. And thank all of you for coming today. I know it's the end of the term, and this isn't always high on your priorities, so I'm glad you're able to make it today. This program was a partnership between TransNow, the Oregon Department of Transportation, Portland State University, and the Portland State University Intelligent Transportation System Laboratory. The evaluation of Comet was actually only part of the study. There was two pieces. The other piece was the evaluation of the ramp meters. Both of the actual finished research documents will be completed by next Tuesday. June 1st is the day we actually have to have them in. So with those of you who are really interested, they're available on our website, and I can give you the address later. So today I'm going to follow this outline. First I'm going to explain our research objectives. And then I'm also going to give you some general information about freeway management in Portland. I've given this presentation a few times, and usually my audience is transportation engineers who are pretty familiar with freeway management. But because we have a lot of planners here today, I'll go into a little bit more background about that. I'll explain to you what incidents are and why we care, why it's so important to be concerned about incidents, what incident response is, the incident response program in Portland. Excuse me. I'll also talk about and display some of the incident data for the region. There's a lot of sort of interesting statistics about crashes and stalls and how they happen. I'll go into the estimation and the costs of incident delay, and then we'll have some conclusions. So our objective, or some of our objectives, were to demonstrate the use and display of archived data from multiple sources for evaluation, monitoring, of freeway operations. ODOT, or the Oregon Department of Transportation, or ODOT, has been collecting a lot of freeway data over the years, and a lot of that data has been going unused. They've just been archiving it and saving it and haven't been really doing very much with it. This is one of the first studies to use a lot of that data and try and extract some useful information from it. Also, our goal was to evaluate the effectiveness of the Comet Incident Response Program. It's been in place for about 7 years now, and nobody has really looked at it to try and figure out how effective it really is. As you will see, it's pretty obvious it is effective, but trying to put numbers to that and quantify it and study that has not yet been done. And then also we want to develop tools to facilitate efficient deployment of resources for programs like this one and other programs in the region and in the state. There's a program in Eugene, and there's also a program that's going to be starting in Salem, and of course people in other parts of the country. There's a number of incident response programs. So first, before I jump right into incident response, it's important to understand a little bit more about the freeway management operations in Portland. ODOT currently operates an extensive advanced traffic management system from the Traffic Management Operations Center, known as the TMOC. This facility has a number of great pieces of technology and gadgets. First of all is the closed-circuit television cameras. They have 75 of those. I'm sure you've seen them. You've seen the images from them probably on the evening news, and those cameras that are mounted all throughout the freeway. Also, they have 18 variable message signs. These are the signs that you see on the highway They're also used to display Amber Alert messages and things like that. Usually they're used to display travel time. It'll say something like 25-minute travel time from Wilsonville, say, to downtown Portland. There's 118 ramp meters. Those are the traffic signals that you see on the ramps that you have to stop and wait. The purpose of those is to break up the platoons of large vehicles coming onto the freeway. And there's been a study done here. Well, there's been a number of studies done, including at least one in the ITS lab, that shows that those really are effective at increasing traffic flow. There's 436 inductive loop detectors on our freeways. Those are these wire loops, and probably you've seen them cut in the pavement. Usually they're round, they're on the pavement. And those loops can detect when a vehicle has crossed over the top of them, a large metal object. It can count the object, and from that we can get information about volume and speed of traffic. And of course we have the digital archives of the incident logs, which was the primary data source for this study. The automatic vehicle location archives of the Comet movements. We can figure out where these trucks were and where they're going, where they've been moving. And of course they have an extensive fiber optic communication system to link all this stuff together. So what do they do with all this technology? Well, one of the best uses of it is for traveler information. As I talked about already, there's the variable message sign here at the top. These variable message signs, like I said, there's 18 of them throughout the region. And in this case, it's warning somebody about interstate bridge repair. It might do travel time. It might do Amber Alert. They're variable, so they can display whatever important information is needed at the time. Also, there are traffic reports. This woman over here is doing a traffic report on the radio. There's facilities actually at the TMOC that they have a television camera, and they also have spaces for actual radio reporters. So there are people actually at the TMOC doing these reports. And then also the traffic cameras, which you've probably seen those on TV. They do traffic reports on television as well. And then another really useful source of information that I think is probably underused, I know a lot of people aren't aware of it when I talk about it, is tripcheck.com. And this website gives lots of information about the highways, not just in Portland, but throughout the state. You can see all of these images from traffic cameras on TripCheck. And just recently, this image that you see on the right displays the speed of the local freeways. So the red indicates that they're either moving very slow or stopped, and then the green is moving at a reasonable pace, usually over 50 miles an hour. Now, aside from traveler information, all these pieces of technology they use can also detect incidents, which is what we're really talking about here today. So what are those incidents? Well, they're crashes, breakdowns, and other random events that happen on our highways. This also includes debris. We've all been going down the road and seen that piece of plywood or box or mattress that's laying in the middle of the freeway. Well, those pose significant hazards, and those are incidents as well, and these are things that Comet will respond to. The incidents can contribute to more than half of the delay on our highways, which, as you will see later on, and I'll discuss a little bit later, incident delay is very expensive. They can lead to major road closures, and more importantly, unplanned major road closures. If you don't know a road's going to be closed and you decide to take that route anyway, you're going to be waiting a long time and be pretty unhappy. And it also increases the driver's exposure to hazardous conditions. As you can see, I don't know what's in this truck, but it's a tanker truck, so it's likely to be something somewhat hazardous, so you don't really want to be exposed to that. Incidents also cause secondary crashes. We've all been on the freeway or riding with somebody on the freeway where you come around a curve and suddenly traffic is completely stopped, and you have to slam on your brakes to avoid rear-ending the person in front of you. Or at least, hopefully, you were able to avoid rear-ending the person in front of you. If you didn't, you would be a statistic and you'd be a secondary crash. It also diverts maintenance resources away from the other things they could be doing, and it reduces the overall productivity. If there's some kind of incident like this that happens, it's going to require some immediate repaving or something like that. Those maintenance resources are pulled away from something else they should be doing. So what's incident response? It's a proactive strategy for dealing with incidents. Prior to incident response, we just kind of waited until an incident happened. And when it did, we thought, oh no, what do? We need to call some maintenance people. We need to call some fire and emergency vehicles. In this case, we're ready. We're here. We're ready to go to deal with these things as soon as they happen. Incident response programs vary a little bit from region to region or city to city. They usually consist of some kind of roving response vehicle, like this truck you see over here on the right. In some cases, in some cities, it will be a tow truck. In some cases, it will just be a standard Department of Transportation vehicle with some extra bells and whistles on it. And in Portland, they're not tow trucks, but they are some very specialized vehicles, which I'll get into a little more. Anyway, they assist all drivers to get them moving again. And this could include This could include a jump start, providing a gallon of gas to get them going, even some very minor mechanical stuff. They're not going to replace your transmission, but they'll do what they can to get you going again. And they can call for additional assistance when necessary. And that would be somebody like hazmat, EMT, fire, police, or even a tow truck if there is a case where they do need a tow truck. So the benefits of these programs, they're the eyes and ears of the highway system, and it's a proven strategy for reducing the duration of incidents. They reduce the delay, fuel consumption, accident exposure, pollution, and other environmental impacts. It also decreases emergency vehicle response times. By virtue of these vehicles being on the road, ready to go, somebody doesn't have to be called and pulled away from something else they were already doing. This is their dedicated job. They get there much quicker. It reduces secondary crashes. In fact, there was a study done in Arizona that estimates this reduction to be as much as 20 to 25%. It also improves the safety for the emergency and the highway maintenance personnel. When these trucks are out there on the road behind an incident with their signs and lights and sirens and flares and whatever the case may be, drivers are much more aware that there's people out there on the freeway. And it also increases, it improves the public relations between the driving public and ODOT. It's pretty hard to be upset with an agency that gives you a gallon of gas to keep moving down the road, particularly at today's prices. So talking about incidents and talking about how they cause delay, and we'll get into a little bit more into delay later, but it's important to understand sort of the life of an incident, what happens when a crash or a stall or whatever occurs, and where that delay comes from. What this is a typical delay curve. The vertical axis is the cumulative number of vehicles passing a given point, and the horizontal axis is the time. And you can see that green line is the demand flow. Most of the time our highways are moving at demand flow. Now, let's say an incident were to happen right here. The flow would be reduced to what's called incident flow, and a queue would develop behind that. So if a lane is blocked, suddenly this backup begins to develop. So a lot fewer vehicles are getting past that given point. Once the incident is cleared down right here, the flow of traffic will move to capacity flow. Now, capacity flow isn't moving at 55 miles an hour. Capacity is usually somewhere between 25 and 35 miles an hour. So it's still slow moving, but they are moving again. And once the queue has dissipated, or that backup behind the incident, it will go back up and reach, again, demand flow. But the result is this shaded area, which is the total delay for that incident. And you can see it's a pretty significant amount. So what incident response does is they try and reduce the amount, or try and reduce the duration of the incident. So imagine if this incident if this incident was cleared at that point. That purple triangle indicates the amount of delay. And you can see it's a significant reduction. In fact, without a geometry lesson, I'll just tell you that reducing incident duration by 1/2 reduces the delay by about 3/4. So time is important. Every second really counts. So incident response in Portland. It's called Comet. Comet is an acronym for Corridor Management Team. Corridor Management Team, CMT, didn't spell anything really good, so they pulled out a few extra letters and came up with the term Comet. Plus, it sounds like they're really fast, so it's great. Anyway, it began in 1997. It now covers the Portland metropolitan area 24 hours a day with 11 specially equipped incident response vehicles. The vehicles usually will go about 120 miles a shift. And back when I first started this study, and it was almost a year ago now, their oldest vehicles had logged over 300,000 miles. So these vehicles are equipped with, as you can see in the picture on the upper right, a variable message sign. That's the thing with the arrow. And sometimes it will display other information about closures or whatever else is going on. But the variable message sign is very useful. It's much more useful than necessarily the person standing there waving their arms to get you around an incident. Basic traffic control equipment, flares, cones, signs, stop, slow, things they could use to direct traffic. In fact, the flare system they have is really kind of interesting. The police are very jealous. They wish they had something like this. I had the opportunity to ride along with one of these Comet operators, and they have it's actually a tube in the middle of the floor of the truck, and these flares are self-igniting flares, and they just push these flares down the tube of the truck. They light themselves, pop right out at the bottom, and they don't even have to get out of the car to drop the flares. It's kind of interesting, although when they do light themselves, the smell of the lighting flares does kind of fill up the cab. But it's pretty neat. But police cars can't actually use those because they don't have enough clearance in their vehicles. So when they drop the flare, it would pop back up into the chassis. But anyway, interesting. It's really an interesting system because especially a driver who doesn't know this, it's kind of odd to be coming up behind a vehicle and seeing these flares falling out of the bottom of it. Anyway, as I mentioned before, they also have gasoline and other automotive fluids, brake fluid, water. People overheat. They can help them with that. Basic automotive tools, screwdrivers, wrenches, whatever it is. Again, like I said, they're not going to replace your transmission, but if there's something they can do very quickly to get you going, they're able to do that. They have a communication system which links them with the TMOC, as I already discussed, but they're also monitoring police, fire, and other channels as well. If there's something that the TMOC doesn't find, but they hear about an incident through the police, they can get there that way. And as I mentioned, the automatic vehicle location system. So at a given time, every so often it reports its location back to the TMOC so they know where all their vehicles are, which can be useful in when an incident is discovered, knowing which vehicle to call that can get to the incident the quickest. Now, even though they have all this wonderful gadgets and stuff on these trucks, what really matters is the people that operate these vehicles. The men and women. There was at least one. I think there might now be 2 women operating these vehicles. They make all the difference in the world. They come up on these people that are stalled, have to crash, whatever it is, sometimes at the worst point in their day or maybe even the worst point in their year given the situation. And they need to be very sensitive, and they also need to know how to deal with these situations. I had the opportunity to ride along with one of these operators, and it was a really, really great experience from 2 standpoints. One was being able to help these people who were in trouble, but also seeing how seriously they take their job and how important it is to them to get these incidents cleared as soon as possible. In one case, just shortly, I rode along on a Friday afternoon. I chose a Friday afternoon because, as you'll see later, that's when more incidents occur. A woman had crashed her car into the median on Interstate 5. And we came upon this incident. It just so happened that on that day, a police officer was on the scene prior to us getting there. And the police officer told this Comet operator, "No, this car's crashed in, the tire's flat, it's disabled, we're going to have to wait for a tow truck, there's nothing we can do." Well, the Comet operator took a look at the situation, walked back to the truck, got out his crowbar, walked over to the car, changed the tire, pulled the fender out, and pushed the car off the freeway. And he did all this in a matter of, maybe 10 minutes. So that car was off the freeway, incident was cleared in 10 minutes. The tow truck was still called because the car couldn't drive anywhere. We came back by that incident at a later time, and the tow truck was just arriving about 20 minutes later. So this operator in one incident alone had saved probably 20 minutes worth of incident duration, which saved, as you saw from that graph earlier, a huge amount of incident delay. And it happened to be at about 4:30 in the afternoon. Also, the thing that made me feel really good, I felt a little like a superhero coming up to help these people. There was a woman stalled on the side of the freeway, and she had 2 little kids in the car. She didn't have a cell phone. She was a long way from an exit, just didn't know what to do. And this operator, it turned out her vehicle was overheated. We were able to give her some water and at least get the vehicle running enough so that she could at least get to the next exit and call for help or do whatever else she needed to do. And I just imagine, myself or my family or my wife and kids in that situation. It makes me feel really good to know that there's somebody out there who's going to help them. And, in terms of a benefit, that's something that's really hard to quantify in a dollar amount, but it's something that's really valuable. So the people are very important. So getting a little more into the details of this program in Portland, this is the patrol region. You can see from the Columbia River on the north down to Wilsonville in the south, way out Highway 26 to the west, and out past Gresham in the east. There's 4 primary patrol regions shown in these colors. A standard shift includes 4 vehicles patrolling these particular areas. Sometimes there's a 5th vehicle sort of that acts as a rover or as an opportunity to sort of give breaks to these other people that are out there on the road. Also, on evenings and weekends, there aren't 4 vehicles on the road, and these patrol areas are sort of combined as needed. So to do some of this study, to do this whole study, we had a number of data sources. Number one and the primary source for all of our data was the incident database. We used automated vehicle location data from the Comet vehicles, some information from automatic traffic recorders that are placed throughout the region, some from the inductive loop detectors. Inductive loop detectors were used more so on the ramp meter report than they were necessarily with Comet. And we also used some archived weather data. So starting with the incident data, the incident database included over 70,000 incident records. Each record includes 72 data fields that give you information about the type of incident, the location of the incident, maybe how many people were involved, the kind of vehicles involved. There's a lot of stuff in there. The first step was to remove almost 50,000 duplicate records. Let me have a sip of water and I'll tell you why. The duplicates exist because the way the data is recorded into the database. So for example, let's say that somebody at the TMOC finds an incident on the freeway. They log into the database that there's an incident on the highway. So that will be the first record for that incident. Then they will call Comet. Comet will arrive on the scene. When Comet arrives, they create another record for that incident. Comet determines that the car needs to have a jump start. They will tell the TMOC. The TMOC will write down that the car needed to have a jump start. Comet will jump start the car. The incident will be cleared, and they will again record that into the incident database. So then you have 4 records for one given incident. So the trick was to figure out how to remove those duplicate records and still keep all the pertinent information that was necessary to be in there. And through trial and error and through a number of different tools, primarily we used Excel and Access and some macros, we were able to extract these duplicate records and come down to a result of about 21,000 unique incidents. From that, I extracted some more information about the number of stalls, the number of crashes. This study also included a more detailed analysis of a section of I-5. So we extracted some more data for Interstate 5, and from that we also pulled out a 3-week sample of data for delay estimation. And a little bit later I'll tell you why we only used a 3-week sample. So from that data, we were able to slice and dice it in a number of different ways, create a number of charts and graphs to sort of analyze and figure out what's going on out there. This is an incident frequency map for the year 2001. You can see the red shows the highest frequency of incidents, and of course green is where many fewer incidents occurred. This map was created using the incidents that were geocoded. Now, in the year 2001, using this particular set of software, only about 10% of all the incidents were geocoded. The reason being, in order for, and I talked about trip check earlier on, trip check will actually show you where significant incidents are happening on the highway. For this incident to appear on trip check, it needs to be geocoded into the system. If they don't want it to appear on trip check, generally if it's a minor incident, it isn't geocoded into the system. So what we're displaying here is only 10% of the incidents from 2001. And these are primarily the more severe incidents because those are the ones that appeared on trip check. So this in itself may not be the best sample of what was actually happening that year, but I think it's still useful to show how this data could be used in the future. One of our recommendations is to geocode every incident that occurs. So if you did have data for every incident, this could be incredibly useful to knowing where you might want to pre-position some of these vehicles, where you might want to have more vehicles on the road. And these could be done by time, by month. It could be a number of different ways. So some other findings from the database and some ways that we can display this data is the incident types. And you can see that stalls accounted for 50% of the incidents in the region. Crashes and debris were the next 2 largest ones. Tag and tow. Tag and tow is when there's an abandoned vehicle on the side of the road. Comet's able to come up and put a little tag on the car and then call a towing company and say, please tow this vehicle as soon as you can. There were a number of other incidents, and that would also include things, construction, congestion, whatever else, other random things that you can't necessarily categorize. But of those incidents, you can see that only about 1/3 of them actually blocked any lanes, and only 3% of those blocked 3 or more lanes. In most cases, 3 or more is a complete highway closure. And then here's another pie chart with incident location. You can see most of the incidents occurred on the right shoulder. Not necessarily occurred, but at least were, when they were discovered, were on the right shoulder. Sometimes a crash will happen in lane. People move it to the right shoulder very quickly. Let's see. Now, however, if an incident is not necessarily in a lane, it doesn't mean that it didn't cause any delay. Sometimes if there's something on the side of the road, people out walking around, people slow down to look, they change lanes, they do a number of different things that can cause a small amount of delay on the highway. Now, crashes and stalls were some of the largest categories, and they account for 65% of all the incidents in the region. And you can see that crashes average lasting almost an hour on the highway, the duration of the incident itself, and that crashes also block almost twice as much lane space as stalls do. So, because crashes are so significant, let's take a little closer look at when these occur. Now, have you ever thought to yourself that it seems like there's always more crashes on Fridays at 5 o'clock? Well, most of us seem to think that, and these graphs seem to show that you might be very perceptive. Now, the difference, at least the crashes by day of week, there's not a whole lot of difference really between the different weekdays, but Fridays are just slightly higher. But of course, the highest crash frequency was occurring during the evening peak, right around 5 o'clock. And I would venture to guess that this chart would look very similar to the display of traffic volumes as well. So likely when there's more vehicles on the road, more crashes are going to occur. So this is a graph of the incidents by type by month. And you can see they vary. Stalls are pretty random. Some of these other things that happen, debris falling off a truck, all that stuff is pretty random. So the month-to-month changes, there may not really be any underlying cause for that. It may be just a random thing. But looking at the crashes, there's things that can cause crashes or maybe increase the risk of crashes. And one of the things I found the most interesting when looking at this was this jump right here between September and October in the number of crashes. So most of you who lived in Portland for a while, can anybody guess what happens here between September and October that might cause more crashes? Anyone have a guess? Rain, yeah. It starts raining. That's usually when it starts raining after a pretty good length of, pretty good period of dry weather. And of course, it seems like everybody forgets how to drive in the rain. So after looking at that, we thought, well, maybe there's something to that. So this is when I went out and extracted some archive data from the National Oceanic and Atmospheric Administration, also NOAA. And we plotted crashes on wet days, dry days, and the number of wet days in a given month. A wet day was any day that had more than a 1/20th of an inch of rain. A 1/20th of an inch of rain, it doesn't sound like very much, but that's just enough to wet the pavement, maybe make it a little more slick. And some of these days also had significantly more rain than that. And you can see, looking back at this month of October, less than half the days in the month actually were wet days, but more of the crashes did happen on those days that were wet. We did some statistical tests and were able to determine that there is a significant relationship between the number of crashes that occur on wet days versus dry days. The days when the most crashes occurred, usually 11 or more, were wet days. Days when the fewest crashes occurred, 3 or fewer, were dry days. So this can also be useful to the people operating this program, or the Comet operators, to know that on wet days, maybe we need to have more vehicles available. Maybe we're going to have a busier day. Maybe we can use our variable message signs to warn people to slow down. So let's just look at one day of incidents. This displays one day when we happen to have 81 incidents this day, when they occurred and the duration. And you can see there's a variety. There's some very, very short incidents, just a little blip. And there's some also very, very long ones. The long ones probably are more likely to be crashes. But to compare this with the number of vehicles on the road, I took these incidents and sort of aggregated them to 15-minute intervals to find out how many incidents were occurring simultaneously at any 15-minute interval throughout the day. And you can see this blue line here indicates the number of incident response vehicles scheduled to be on the road. Overall, they've done a pretty good job. If we could just get these people to schedule their incidents just a few minutes later, we'd be in really good shape. But again, these are really random things, and it may not be cost effective to necessarily have 6 vehicles out there on the road when they don't have other things going on. So this was really useful and very interesting, and I thought, wow, this would be great if we could do this for an entire year. How could we do that? Well, with the assistance of Andrew Bird, another student in the ITS lab, he helped me figure out a way to extract some data and manipulate it in such a way that we could do this for an entire year. Now, what you're seeing here, it's a little bit messy, but let me find it here. Okay, this graph shows the average number of ongoing incidents by day of week at 5-minute increments for the year 2001. Now, to clear that up just a little bit, we'll start by looking at this spike right here. This happens to be a Tuesday, and I did this by instead of just choosing a weekday, I chose all different days because Fridays can be very different from Tuesdays. There's some variations. Overall, they have a similar shape, but there are differences. So just looking at this spike on Tuesday, this means that for the year 2001, there were an average of slightly more than 4 incidents happening simultaneously at about 9 o'clock on Tuesdays for the entire year. This happens to be, okay, and then if we overlay that with the scheduled incident response vehicles to be on shift, you can see that that's the only point where there's actually an average of more incidents than vehicles available to assist with those. This may be an anomaly from just this year. I don't know. We would need to look at. It would be useful to look at this, look at more years of this. But this would be very useful to the Comet operators to determine their staffing levels. And you can see they've really done a pretty good job. What they might want to do is bring this this last vehicle on a little bit later and keep it on a little bit longer, and they'd be in much better shape. And then also, this is Saturdays and Sundays, and those are also very different from the weekdays. And the Comet shift, the most they have on Saturdays and Sundays is 2 vehicles. And they've done a pretty good job, again, having vehicles available to assist in these incidents. Right here, this area right here, that's when there's no vehicles on the road. We have to give them a break sometime. They can't be out there all the time. So now the incident delay estimation. This was a more difficult, this proved to be a more difficult task than we thought it was going to be originally. So first we took this 3-week sample of incidents, and this 3 weeks was, I forget the exact dates, but it was the first 3 weeks in November, just before Thanksgiving. So there were no holidays involved with that. So we had these 660 incidents, but we had to filter them down because there were a number of incidents in there that were, they were test records, they had no duration, they were maybe off the freeway network, which is what we were really trying to look at. So we filtered this down, and there was only 164 delay-causing incidents after that. So using those incidents, I manually matched the incident location to the automatic traffic recorders. I didn't want to do this manually. We had to do this manually because of the way the data is recorded. I talked about this incident database having 72 different records, and some of the records being location by freeway and cross street. Well, these are entered as text, and each operator seems to have a different method for the text they like to enter for a freeway. So one person for Interstate 5 might put I-5, one might put I-5, one might put 5. You never know. And then for the cross streets, you don't really always, there were some cross streets that were spelled incredibly poorly. There's no spell check in this database, apparently. So anyway, I had to manually match all this stuff, and basically I ended up using GIS and finding where the incident was located. So I had to manually match these, then find the closest automatic traffic recorder to determine the volume of traffic. Let's see if this is the next one. No, I'll get to that in a second. So we also determined the capacity reduction using the incident data and tables from the highway capacity manual. The highway capacity manual tells us that if you have 3 lanes of traffic, one of the lanes is blocked, the capacity of the highway is reduced by this specific amount. And we just use those numbers that they gave us. Now this is back to the point where I used that data that I manually matched. So we had the average flow data for a specific hour of the incident was drawn from the automatic traffic recorder database. So if at 2 o'clock in the afternoon on a weekday, we were able to determine that past this given automatic traffic recorder, there was usually X number of vehicles passing by. And I tried to do it hour by hour to try and come up with a more accurate estimate. So the result was 112,000 vehicle hours of delay caused by incidents during this 3-week period. Using an equation from General Motors that talks about an equation that estimates the amount of fuel used in slow-moving vehicles and stop-and-go traffic and the average cost of a gallon of gas for that particular year, we were able to estimate the cost of additional fuel at about $150,000. Then the estimated cost of lost time was $2.8 million. Now this was estimated using the average wage rate for the region for that year and also the average vehicle occupancy of the vehicles in the region for that year, which the average vehicle occupancy, that was a number that came from ODOT, and their number, I think it was about 1.3 persons per vehicle for that year. So the total estimated cost of delay for that 3 weeks was almost $3 million. Like I said, delay is very expensive. So to extrapolate that out to a full year, we come out with almost 2 million hours of vehicle delay. The estimated cost of the additional fuel consumption, about $2.5 million. Total cost of lost time, almost $50 million. And the total estimated cost of the incident delay is $51 million. Now keep in mind, this is just incident delay. This isn't your standard congestion. This isn't your recurrent bottlenecks. But also, this was happening while Comet was on the road, trying to reduce delay. We didn't have data from before Comet was on the road. So trying to actually attach a dollar value to the amount of delay they reduced was actually impossible. So we went at it a different way. If each incident were to increase in duration by an average of 1 minute, the annual cost of delay increases by about $1.4 million. The cost to operate Comet for a year is about $750,000. So if you do the math, you can determine that for Comet to be cost effective, the duration of each incident needs to be reduced by only 32 seconds. Now, this is just to recover the costs in terms of delay cost. There's all these other benefits that we discussed of saving somebody from the side of the road, environmental impacts that aren't included in this. But using this 32-second number, we were able to generate an efficiency curve. And you can see up and to the right, the benefits are greater than cost. Down to the left, costs are greater than benefits. Comet is not able to assist in every incident. That 32-second number is assuming they were able to assist in every incident. According to the incident database in the year 2001, it said that Comet was able to assist in about 43% of the incidents. Now, due to the way that data was recorded, I suspect they were actually able to assist in more. But using that 43% number, we can come over to this curve and go down, and we can see that in order for them to be effective, they need to be reducing the duration of each incident by just a little bit more than a minute. So in conclusion, Comet is clearly beneficial. The responders need to reduce the duration of each incident by just a few minutes in order to have a positive effect on the flow of traffic. Now, because they are on the road, because they're dispatched through the TMOC, they're usually able to get to incidents a whole lot faster than previously. In fact, just earlier this week, I spoke to a former Portland police officer who was working when Comet first went into operation in 1997. Prior to Comet, they were often called out to assist in these incidents. After Comet started, he said that in most cases, Comet had the incident cleared or was already on scene before they were even made aware that it happened. So you can see that right there, we're probably looking at 5 or 10 minutes delayed reduction right away. Also, like I mentioned, it's impossible to measure and assign a dollar value to the numerous other environmental, public relations, and other benefits of the program. I like knowing that Comet is out there to help me if I have a problem, and I think probably most of you like that as well. The archive data is a really rich source of information, and I think it should continue to be used. You can see we were able to generate all these charts and graphs from this data, and as the recording methods of the data and the type of data recorded improves, it's only going to get even better. And like I said, ongoing improvements to the database entry and dispatching need to be made. One of the major recommendations was geocoding everything. We want to know where all this stuff happens. In real estate, you always hear people say location, location, location. Well, in transportation, I always hear Dr. Bertini saying location, location, location. We want to know where this stuff is happening, and that makes it useful for us to display this in different ways and to measure benefits and costs. And with that, I'm going to end. I'd like to thank all these people listed here. One person that's not on there is Darren Branham, who was the Comet operator that I rode with that day. I really appreciate that he was willing to let me ride along with him and just pester him with questions all throughout his shift. And also the full report for this is available online at this website right here. And the ITS Lab is doing lots of other great stuff. So feel free to visit the ITS Lab website, and you can see some of our other reports as well. So with that, I'll take any questions you might have. Justice?
I was wondering what sort of things had to be done in order for this program to be started. How much capital had to be put down, and preparation, and maybe what sort of things the city would need to break even or to need this sort of program.
Well, like I said, the program started in '97. I spoke with Richard Santana, who currently runs the program. Interestingly enough, he was hired on Valentine's Day of 1997, and the Comet was in operation, or the Comet system was in operation a month later. The original outlay, I don't have the number for what they originally spent to buy the initial vehicles and everything else. A lot of the detection equipment was already in place. They already had a lot of these cameras. They had a traffic management operations center. A lot of the stuff was already there. And you know, the cameras serve more than one purpose. I mean, they're used for a number of different things. So that was in place. The program, I had a number there. I think the number was about $17 million. I think it's cost about $17 million since its inception in 1997. Because they have a lot of this equipment in place, the costs have reduced a little bit over time. And then also, and I don't have, I guess I really can't quantify it, but you need to have a certain population and a certain amount of delay to make it worth, you know, reducing. I mean, obviously, you're not going to start a program like this probably in Baker City, but they do have one in Eugene, they're going to have one in Salem, and they do have one in Portland. Does that answer your question? Okay. We'll go with Michael first.
You mentioned earlier on something about pre-positioning, and I'm just wondering, as you've mentioned many times through here, that each second counts, and you know, when an incident happens, it gets compounded so quickly. And I was just wondering, you showed the map where the trip check map, and you could see where the real heavy points of incidents are.
Right.
And I was just wondering, do you think it would make sense to have maybe a truck not even roving, but actually maybe situated somewhere in that high incident area, maybe as close to a freeway on-ramp as possible, and so that when an incident like this did happen, it could get right to it maybe a little quicker? I'm thinking in terms of, and I don't know, I mean, you could tell me if this is true, but it seems like maybe a truck a lot of times will get caught in delays because maybe there's inadequate shoulder space at some spots and things like that.
The vehicles do have, and I guess I didn't mention this, but the operators are trained in EMT. They take an emergency management driving course or an emergency driving course. Anyway, they have lights and sirens, so they can, you know, they can fly down the road and fly through traffic. And the day that I rode along with Darren, we did that on more than one occasion, and I was surprised at how quickly he could get through traffic. I really thought he would come up on stuff, and I thought, boy, there's no way we're getting through here. And the next thing you know, we're weaving through it, and we're on our way. So it seems like they can get where they need to get pretty quickly. As far as pre-positioning stuff, at this point, they're not really doing that, but I have seen a number of times one specific Comet vehicle stopped on actually right about at this location on that overpass near the zoo. And I suspect that probably she does that because it happens to be, that particular area happens to be one of the women of the program who actually runs that particular route. But I suspect that she does that because the traffic there is usually so heavy that she ends up just sort of getting stuck in traffic and really can't get to where she needs to get. If the incident happens on the other side of the freeway, she's got to get off and get back on and get over there. She just sits on that overpass. She can wait for it to happen. And if you've been in Portland long enough and you've listened to the traffic reports, you can pretty much guarantee there's going to be an incident somewhere around there almost every day. So I don't know if that's necessarily a planned thing that they tell her to do, or if she's just through her experience in being in that area, she's figured out that's the best way to handle it. Does that answer everything you asked? Okay. Jerry?
About two-thirds of the way through the presentation, you showed a diagram, it was kind of hump-shaped diagram showing incidents over the day.
Yeah, was it this one?
I think it's the bottom center.
This one?
Yeah. And you overlaid it with the number of vehicles being deployed during those times.
Right.
Just to suggest there's some kind of efficiency going on in terms of their allocation of resources. But the accidents that occur during rush hour, when there are a lot of cars on the road, are much more costly in terms of delay than the accidents that occur in the middle of the night. And so I would think from my point of view, you'd want to ratchet up or multiply all of those accidents during rush hour by a much higher factor in order to come up with an estimate of cost per time. And then I guess the other question would be how effective. So the costs to me are kind of misrepresented by by that diagram, all beautiful as it is. And then the other way, and then the benefits, I think, also have to be thought about a little differently as well, because what's the benefit of the fifth Comet or the sixth Comet vehicle on the road?
Yeah, and actually that's a good point. I didn't really think about sort of weighting the incidents in that manner. I mean, in this graph, each incident is treated with the same weight. What else I would think would be nice is if people didn't assume that they needed to work in an 8-hour shift or a 4-hour shift or whatever the shift may be. It's pretty difficult to call somebody up and say, go drive Comet for 2 hours and we're only going to pay you for 2 hours today, or find something else for them to do. So a lot of the way these shifts work are sort of tried to fit around 8-hour days.
The management question for ODOT is presumably, if you do get an extra $50,000 in your budget for Comet, how do you apply those extra costs, or where do you hire people for?
Right.
I was just saying, a simple look at that diagram, from my point of view, would be misleading.
Yeah, you're right. It could be. One thing that I discussed in the paper is that, or in the final report, most of these Comet operators also work in the TMOC, actually recording the data and dispatching people as well. So, and again, I'm not exactly sure how this would work, but on a given day, if they really need more help, they might be able to take somebody from the TMOC and get them out on the road. And I would think that not that it's an easy job to sit there and log all these incidents, but I would think that sometimes having more people on the road might be more valuable than having more people logging the data back at the Traffic Management Operations Center. So that might be one way they could get at having somebody out there for a very short period of time to help when it's necessary. But thanks for your comments. Back there.
This is kind of basic, and maybe you went over this and I missed it, but how is Comet notified of the incidents? In what ways?
Well, a number of ways. The Traffic Management Operations Center has cameras. They have loop detectors. Citizens can call in and say, "Hey, there's a crash," and sometimes they just happen upon them themselves, just because they're out there on the road. Usually it's through the cameras, but also this speed map that I showed earlier. It's actually a ways up, but that speed map, it changes every 20 seconds. So let me get back up to it again. Right here. This speed map changes every 20 seconds. So if it's all green, we know that everything's going just fine. But a person in the Traffic Management Operations Center sees something that looks very similar to this. So if they look up and suddenly see a big red line go across this thing, or a yellow line, but they're not really sure what's going on, they can immediately go to the nearest camera, look around, find the incident, and then call Comet. So, but it's usually through the TMOC. Did you have a question up here?
Yeah, as far as the costs associated with delay, did you include the costs associated with freight that's stuck in traffic, or is that in addition to that figure?
That would be in addition. Like I said, we use the average wage rates for the state. So the cost of delay is different for every person. I mean, somebody who's going to visit grandma, getting there 5 minutes later might not be a big deal. The guy who's driving the FedEx truck who needs to get his delivery there by 10 o'clock, the cost of delay might be a whole lot more, or a person who's late for work, or a person who's late for daycare. We've seen in transportation, we always use that as an example, picking up their child for daycare. So the costs are very different. It's just it's a very basic evaluation. Tony?
In terms of the average wage rate, I think ODOT has found that the average wage for people commuting in the Portland area is about twice the average wage rate for the state. So you might want to take a look at that relationship in terms of your benefits. But I was also wondering about the issue of the average incident response time. Basically, it would seem that the speed with which the truck gets to the site, or the amount of time involved in that, would be almost as important as the time that it takes them to clear the site, and that would then relate to things like the variance in terms of the number of incidents per day or per hour and so on. Is there any way of looking at that and looking at how you would optimize the response time?
Yes, that's a really good question. The incident database does not tell us how long it took Comet to get to any of these incidents, and that's another recommendation for the future of their incident database. And they're going to be actually upgrading their software very shortly. However, something that does get at that a little bit is they used to give comment cards to everybody they assisted, and one of the questions on the comment card was how long did it take for Comet to get to you? In most cases, they marked that it was less than 5 minutes for Comet to arrive. They no longer give comment cards because the comment cards were overwhelmingly positive, and they didn't see the point in printing up the cards and paying for the postage anymore to just hear about how much they helped somebody. They realized that they were doing pretty well. So I guess what that tells us is they are getting there pretty quickly, and it would be nice in the future, and we recommend in the future of somehow recording in that incident database when the incident happened and how long it did take for Comet to arrive, and then maybe optimizing that as well. And then also knowing where the vehicles are at all times through that AVL system becomes useful as well. Even if an incident happens in the western patrol zone and the Comet truck happens to be way out on the western side, yet another Comet truck in a different region is much, much closer, it obviously makes more sense to call that truck to get to that incident first. But that's stuff that needs to be optimized throughout the system, and also the data needs to be recorded. Robert?
Actually, I think 5 or 6 email questions, but I'll try to distill them down because you've covered some of them, I believe. But one viewer asks or points out that, of course, traffic volume is increasing over time, and so we would expect the number of incidents to increase over time. So he asks whether there is an analysis of future demand for an increase in the number of Comet vehicles on the road, and along those lines, is ODOT planning to increase Comet activity?
Well, first, thanks. I'm thrilled to get an email question. Not everybody does. But, yeah, that's great. Anyway, at this point, no, we didn't do an analysis of future demand. But as you can see from the pretty graph that Jerry liked, but also pointed out the limitations of, if we were able to look at that every year, and the way we've set this up, it will now be very easy for the Comet operators to take that data and sort of generate that on a weekly, monthly, or yearly basis. You can, I'm assuming you'll be able to watch over time that the number of incidents is going to increase. And they do have enough equipment available to increase the program as necessary when that comes about. Did that answer the whole question? Okay. Ariane?
So usually it's your responsibility as an automobile owner to keep your vehicle in good working condition and make sure you have enough gas and stuff. Do you think that having these roving vehicles that will get you out of trouble at no cost to you will make people less responsible?
That's a good question, and I'm going to steal something from Dr. Bertini that I've heard him talk about before. First of all, probably not, because running out of gas on the freeway, something you don't really want to do a lot. You don't want your car to break down a lot because it's going to be expensive. And like I said, they only do some very quick repairs, and these people aren't auto mechanics, so I don't know that I want them tinkering around under my hood too long. I just would like to just enough to get my car going again. However, the program and maybe Robert can tell me for sure, I believe it was in San Francisco or in Los Angeles, they had one driver who just seemed to use Comet as their gas station. He just would run out of gas all the time and wait for them to come to give him gas. And finally they got upset and they said, "That's it. We're not helping you anymore. We're not going to do anything." So that was when they got their first really nasty comment card back that they didn't like the incident response program. Jennifer?
I have a question. Maybe it gets back at what Jerry was discussing, and maybe not. But the point of that a delay at 5 o'clock on Friday, an incident at 5 o'clock on Friday, is going to have a bigger impact on the system, presumably because there's more traffic then, right? So when you were calculating, when you took your incidents, your 600 and whatever incidents, and then you said you linked them back to... Did you link them back to the actual traffic on the road, volumes on the road at that time, on that day?
Yes, I used the average for the year, but yes. So it was looking at 2 o'clock on say the incident happened at 2 o'clock. It was looking at 2 o'clock on a Tuesday afternoon on that particular stretch of highway.
So in theory, your estimate of the hours of delay, those things that happen at 5 o'clock on Friday are a bigger portion of that than 2 a.m. on Sunday?
Yes, they are.
I hate to barge in, but the the focus was on delay causing incidents. So incidents at 2 in the morning probably weren't delay causing, so we filtered those out at the beginning. Last question.
Sure.
And I'm going to try not to laugh when I ask this question. But you mentioned the use of water for vehicles, but I believe the Comet vehicles also provide bottled water for passengers who are, on hot days and things like that. And do they provide anything else, like for kids in the vehicle?
Yes. Yes, they do. They'll have stuffed animals or toys of some kind, because if you're like this incident we saw at the that I saw that day, these 2 kids were in the back of the car. They were pretty scared.
Would you like a visual aid to more explicitly describe what you're talking about?
Sure. Sure. Why, thank you.
So let's thank Mike for a great presentation. And also congratulate him on the latest addition to his family. And I think we have 2 Comet bears there, one for each of the Rose children.
Do you really? Oh, you do? This is great.
Thanks to Chris Monsieur for picking those up from ODOT.
This is great. Thank you,
And thanks
Chris.
again, Mike.
All right,
Good job.
thank you very much.